Hello everyone, this is lecture 4 of unit 3 real analysis and we are seeing about the topic of limit. The last class we have seen that was the sequential criteria for existence of limit, and we have seen that if we have a sequence xn converging to C, then the image sequence f of xn converging to the limit L if the limit existence, and whenever we have a sequence xn converges to C, f of xn converges to L, then we also that the limit exists. But this theorem is used mostly to show the non-existence of a limit. How is it? I am writing the note. The first point, if I have a sequence xn, if xn and yn are two sequences in D minus C such that xn and yn both converges to C, but f of xn, the image sequence, and f of yn converges to different limit, then we say limit x tends to C, fx does not exist. Okay, so if we have two sequence xn and yn converging to C, but the image sequence converges to two different limit, then we say that the limit does not exist. And we'll see certain example for this one. And okay, first one example is, so that limit x tends to 0, fx does not exist, where fx is equal to sine 1 by x whenever x is not equal to 0. Okay, so here we have fx is nothing but sine 1 by x whenever x is not equal to 0, and the c is nothing but 0. To show non-existence, we find two sequence xn converging to C and yn converges to C, 0, that means 0, but the image sequence converges to two different limit point. So just I am writing the sequence. Let xn is equal to, I take sine n pi is 0, so I can choose x is nothing but 1 by n pi by n, so the sine 1 by x, sorry 1 by n pi, xn I have chosen 1 by n pi. Now whenever n tends to infinity, xn converges to 0. Now what is that f of xn? Is nothing but sine 1 by xn is nothing but sine n pi, and that is nothing but 0, 0, 0, 0 is a constant sequence which converges to 0. So xn is a sequence converging to 0, f of xn converges to 0. Now let yn is equal to 2 by 4n minus 1 pi. Why I am writing that 4n minus 1 pi is from the trigonometry. I am just recapping this one within the 1 minute. We know that sine 0 is 0, sine pi is 0, sine 2 pi is 0, sine 3 pi is 0, sine n pi is 0. But this is sine pi by 2 is 1, sine 3 pi by 2 is minus 1, sine 5 pi by 2 is 1, sine 7 pi by 2 is minus 1. So here we have pi by 2, 5 pi by 2, 7 pi by 9 pi by 2, and this all, and this is of the form 4n plus 1 pi by 2, and here we have 3 pi by 2, 7 pi by 2, 11 pi by 2, all these are from 4n plus 3 pi by 2 or 4n minus 1 pi by 2. That's why I have taken yn equal to 2 by 4n minus 1 pi. No doubt, whenever n tends to infinity, yn converges to 0. But what about the f of yn? Nothing but sine 1 by yn sine 4n minus 1 pi by 2, and that is nothing but minus 1 minus 1 minus 1 minus 1 and so on, and that converges to minus 1. So we have two sequence xn and yn. Here we have xn and yn converges to 0, but f of xn converges to 0 and f of yn converges to minus 1, converges to two different limit point, So you can say that limit x tends to 0, fx does not exist. Okay, so we have another example. Fx equal to bracket x, so that limit x tends to 0, fx does not exist. Not about the 0, this limit does not exist even at every integers. So I have taken 0, I can take this 1, 2, 3, okay. So again I will take a sequence xn is equal to 1 by n plus 1. So n tends to infinity, xn goes to 0. F of xn is nothing but the bracket integer, greatest integer function 1 by n plus 1, and 1 by n plus 1 is strictly less than 1 for n belongs to natural number. So this is less than 1 and positive number. So this is nothing but the 0, 0, 0, 0, and it converges to 0. Again take yn is equal to minus 1 by n plus 1 or minus 1 by n, I can take n plus 1. Okay, here again yn goes to 0, but f of yn is nothing but minus 1 by n plus 1 and it's a negative number, that is minus 1 minus 1 minus 1 and so on, and converges to minus 1. So here we have two sequence xn and yn. Xn and yn converges to 0, but f of xn and f of yn converges to different limit point, So I can say that limit x tends to 0, fx does not exist. Okay, if the question is that limit x tends to 1, fx does not exist, how can I show that? In place of xn, I will take it 1 by n plus 1 plus 1. Now xn converges to 1. F of xn is nothing but 1 by n plus 1 plus 1, and it converges to where? 1 comma 1 comma 1 comma 1, that converges to 1. And y1 I will take it 1 by n plus 1 plus 1. Again yn converges to 1, but f of yn converges to 0. Okay, so we have two sequence xn and yn converging to 1, but f of xn and f of yn converges to two different limit point. So I can say that f of xn, limit x tends to 0, f of x does not exist, or limit x tends to 1, fx does not exist. Now another example, this is a beautiful example. Limit x tends to 0, signum of x, signum function does not exist. First of all, what is the signum function? Signum of x is nothing but 1 if x is positive. Positive means strictly greater than 0. 0 if x is equal to 0, it is minus 1 if x is less than 0. So I have to show that limit extends to 0 does not exist. So again I will find the two sequence xn and yn converges to 0, but f of x and f of yn converges to two different limit. Here simply xn, I will take xn is equal to 1 by n, converges to 0. Yn I will take it as minus 1 by n, this also converges to 0. Was it f of xn? Nothing but simply 1 by n, signum function, signum of xn, and xn is positive because 1 by n. That's why this is nothing but the 1 is a constant sequence, converges to 1. F of yn is nothing but signum of yn, and that is a negative number. That's why it converges to the constant sequence minus 1 converges to minus 1. So we have xn and yn converging to 0, but f of xn and f of yn converges to two different limit point. So simply I can set limit x tends to 0, fx does not exist. Now I am giving a task that so that limit x tends to 1, fx exist for this function. Okay. Now there is another theorem which shows the existence and non-existence of limit. So I writing the theorem, just wait. So this theorem says that D be a subset of R and f be a function from D to R be a function. Let C be a limit point of D. If f has a limit L belongs to R, means the existence of limit is given at x equal to C, then we will show that f is bounded on a neighborhood of C, intersection with D. Proof that first of all some of our student doesn't understand why we are taking the intersection with D. Let's see, let I explain this one. C रो neighborhood वाले करा हुआ something C minus epsilon C plus epsilon. जरूरी नैनो कि ये सब point रे function टा define थीबा. So we are taking those point. If I take the intersection with D, then we will get those point of the neighborhood where the function is defined. That's why NC intersection with D is taken. Okay. Given limit x tends to C, fx is equal to L. Need to show that fx is bounded in the neighborhood, this one. Okay. Bounded in the sense that fx mod is less than something b positive number for all x belongs to the NC intersection D. If I take any point in this neighborhood, then fx is less than a particular b. Okay, we find that b. Okay, so let choose epsilon is equal to 1. Now I can choose epsilon is equal to 1 or epsilon equal to 2 because for every epsilon this is true, limit existence. There exists a delta positive such that mod of fx minus L each less than 1 for all x belongs to the deleted neighborhood of C intersection with D. Deleted neighborhood of C intersection with D. Now we have more one thing, that inequality where mod of fx minus mod of L raw mod is less than equal to mod of fx minus L, and that is less than 1. That means mod of fx minus mod of L raw mod is less than 1. That means that minus 1 is less than mod of fx minus mod of L is less than 1. So fx mod is less than mod of L plus 1. I can say that. That is true for all x belongs to the deleted neighborhood of C intersection with D. So if I say that if x does not belongs to D, then that sorry if C, because C dx roche, C that D rehi pare kimba C that dx roche, C that D rehi pare nahi bhi pare. If C does not belongs to D, then mod of fx is less than mod L plus 1 for all x belongs to the neighborhood C delta intersection with D. C is not in the D, then I do not need to write the dex here. If C jodi D re thiba, domain re thiba bele, this all thing, this statement is true for every point, every neighborhood of C intersection with D, and we have that C is deleted here. This all thing. If C belongs to D, then let B is equal to, I will take as maximum of mod of f of C and mod L plus 1. If C belongs to D, C is means D domain define hoche, means f of C exist koru thubar kotha. Dekho baki C ke chhari kori function ro value kahano less than mod L plus 1 ru less than hai. To gote point chhari gala C point function ro value ta kete f of C. So I will take the B is equal to maximum of mod f C, this one. Jenda maximum hoba somostonk lagi kaam kori jiba. Hence mod fx is less than that B for all x belongs to the neighborhood of C intersection with D. This shows that f is bounded on some neighborhood of C. The function is bounded on some neighborhood of C. Here there is small deduction that, just note, I am writing just simple note that if fx is unbounded at some neighborhood of C, then I say that we can say that limit x tends to C fx does not exist. If the function is unbounded at some neighborhood of a point C, then at that point the limit f of x does not exist. We give a simple example that limit x tends to 0, 1 by x does not exist. Since fx is equal to 1 by x is unbounded on every neighborhood of 0, not a single, every neighborhood of 0, fx equal to 1 by x is unbounded. Hence I can say that limit x tends to 0, 1 by x does not exist. Okay, in the next lecture we will see some sign preserving property and some maximum minimum property, algebra of limit and rest in the next lecture. Thank you.